Okay, so a little section here. So something I can ask you to do is calculate the work done by force. And I understand you understand from other modules that the area under a force distance graph is the work done. And we'll just show this very quickly. I think it might have been in your maths module last semester as well. So take some kind of a curve describing a force applied over a distance. Okay, should label this. And let's look between A and B. Okay, so what we're going to do is we're going to split up the region. So we're interested in the work done between the points A and B. So we're going to split this up into so many pieces. Now I'm going to work, well, we'll see. Okay, so let's split it once, split it again. Split it again is probably enough for our needs. So we're going to say that the work done, say we'll look at the fifth one, for example, 1, 2, 3, 4, 5. We'll say that the work done between here and here, between those two distances, is W5. And so you have the work done between the first point and the second and the third, etc. You have the total work done between A and B is equal to the work done between, well, let's say this is x1, x2, x3, that's x4, x5, x6, x7, x8, etc. So the work done, say Wi, is work done between xi minus 1 and xi. So, you know, something's pushing something from A to B, and if you break it up into little regions, the work done will be the sum of the works over the mini sub-regions. Okay, so that's the first thing. Now what we can do is we can approximate the work done as follows. You take a point, say the midpoint of the little subinterval. This one I think would be called 1, 2, 3, 4, x5 star probably. And you calculate the force at that point, and then you make a rectangle. Now the area of the green rectangle, well, what about it? Okay, so what are we saying? What we're saying is that if you look at that region, you've got the force at x5 star times the distance, which is, now we're going to say the distance between all of these is delta x. So delta x is the width of one of these. So if I do force at x5 star times distance delta x, I have an approximation of the work done. Now it's not a perfect approximation because so if I calculate here, so the force here is f of x5 star. The force is not constant. Like you can see, the force is variable, and even over that little region where the work W5 is done, the force does vary. It's well, if you zoomed in, so at this initially the force is bigger than x5 star, and afterwards it's less than. So, but it's an approximation of the work. Would be the force f of it. So I'd say W5 is approximately the force at the midpoint times the width. That's just force by distance. Okay, and so you get that the work is approximately the force. Now these are all these x1s, etc. are really little stars. They're little midpoints. And here we were saying n is equal to 8 in the way we drew it. Now this thing also approximates the area, because if you do the force by the distance, that's the area of that green rectangle, which approximates the area of the strip. And all of this can be made more accurate if you take the number of strips going to infinity. And that ends up being integration. So you get the limit as, so n would be the number of strips. So I'm just going to hashtag strips, number of strips, goes to infinity of this thing here. I equal to 1. Number of strips, we're going to call it, so let n be number of strips. And the force by the distance. So this becomes a better approximation to the work, but it also becomes a better approximation to the integral, which is the area. And so you just take that second bit there, that work is the integral of force. Okay, and you can actually understand this sigma as a sum. It's letter S, it stands for sum, and dx. Now if you think about, if there's loads and loads of strips, the width of them, the delta x, becomes really, really small, and delta x is actually a capital Greek D, and the idea is that if it gets really, really small, you go from a capital D to a little d. So in this sense, I don't know how much you've done on this, but integration being an infinite sum, it's more from last semester. But anyway, all you really need to know is that work is the integral of force in the force distance graph. And if you understand it as, oh, I know that work is the area, well, of course, the point is the area and the integral are the same thing. Okay, so that's the theory. I think we're just going to look at one example. So it's very likely that I'll ask you to calculate the work done by a force where you will need to use either integration by parts or complete the square. So in this one, we'll see an example where it's probably integration by parts. Because you should know that the 1 over the x squared will be inverse tan, complete the square. 1 over square root minus x squared will be complete the square inverse sine. So the work is the integral. So we're going from O, which is a distance. So what do we got? Suppose that the force an object at a distance x from a point O. So you got some point O, and you've got a formula for the force at a distance x. And so we're trying to go from O to a distance 15 pi. So here, well, here the distance from O is 0, so you're trying to go from 0 to 15 pi. So that's what you're integrating over. The force, which is 10x sine x dx. And you'll get marks for just writing that down, by the way, to know that the work is the integral of the force. Now this is going to need integration by parts. How do we know that? In the context of this module, you know, because I'm going to be examining it, but more generally, if you look at it, you can't just anti-differentiate term by term here, because they're multiplied together rather than the sum. So we can't differentiate term by term because they're multiplied together. Next thing is the manipulation. There's no real manipulation here. And then the substitution. There's nothing really you can do because the substitution should be inside something else. And the only thing that's inside something else is the x. But you're never going to do a w equal to x substitution because all it does is change all the x's to w. Is a big waste of time. So you're going to have to do integration by parts. And I recommend with an integration by parts with limits that you forget initially the limits. So we're going to look at the antiderivative 10x sine x dx. Now what we'll do now is, if we're doing integration by parts, we'll write down the formula, which says antiderivative u dv is equal to uv minus antiderivative v du. Okay. You could take the 10 out as a constant, either at this point or in the line above when you write down the work, but we'll just run with it. Okay. So we have to pick the u according to Liate, and then everything else is dv. I'm afraid I can't remember the colors that I used to use. So u. So is there any logs here? No. Any inverse trig? No. Algebraic? Yes. The 10x. So this should be the u, and everything that's left over is the dv. Okay. So look at the formula. So we want I equal to u, which is 10x, by v. So how do we get from dv to v? Well, we remember that v is the antiderivative of dv, or the integral of dv is probably more accurate, but whatever way we think about it. So we need to anti-differentiate sine of x. You go into your tables and the antiderivative of sine of x is minus cos of x. Now when we're multiplying by a negative, we should use a bracket like that. Minus antiderivative v again, which is still minus cos x, by du. Now how do we get du? We differentiate both sides of u. So if u is equal to 10x, differentiate both sides, you get du dx is equal to 10 by 1, which is 10. Multiply both sides by dx, you get du is equal to 10 dx. And for space here, we'll probably be okay. So I'm going to tidy this up a little bit. So we've got plus by minus, which is minus. And then in the thing, in what's left, we've minus by minus, which is plus. And then you can take out the constant 10. You're left with 10 antiderivative cos x dx. And then this should be okay. So the integration by parts doesn't do it completely. You do it in parts. So that's the first part done. The second part is to calculate the antiderivative cos x dx. But that's simple because the antiderivative cos x is just in the tables. It's sine x. So you get minus 10x cos x plus 10 sine x. So that is the antiderivative of 10x sine x. So now we can go off and calculate the work, because it's the integral from 0 to 15 pi. Remember, we have to be in radians. 10x sine x dx. And so how do you calculate an integral? You antidifferentiate, and we've done the antiderivative. So the antiderivative is just above the square brackets there. Minus 10x cos x plus 10 sine x. And we're going from 0 to 15 pi. Okay, and now we do top limit minus bottom limit. So putting in 15 pi, so minus 10 by 15 pi by cos 15 pi plus 10 sine 15 pi minus, substitute in the bottom limit, so it'll be minus 10 by 0 cos of 0 plus 10 sine of 0. Okay, and now you can go into the calculator if you want with this, but it's possible to do a little bit better. So the minus 10 by the 15 pi is minus 150 pi. Now 15 pi is it's 14 pi plus 1 pi. Now 14 pi, because 2 pi is a full revolution, so 14 pi is 7 revolutions plus half a revolution. So this is actually cos of pi. It's actually cos of 180 degrees. Now if all that's gobbledygook, you just go into your calculator. Cos of 180 degrees is minus 1. The next thing, then sine of 180 degrees is actually 0, so that's 0. Then you've got minus 10 by 0, so it doesn't matter what happens, that's a 0, and you've sine of 0, which is also 0. And so you end up with minus 150 pi by minus 1, which is plus 150 pi. Now for me, we'll have to go and think about the units here. You might like to keep the 150 pi, I would, but we'll go with what you might like. So this is approximately 4 significant figures, 471.2. Now it's, look at the work formula up the top. The sigma, or the S, is just adding up, and it's a force by a distance. So the unit should be units of force by units of distance. And the units of force are kilonewtons, and the distance is meters. So this is kilonewton meters. If you want to convert into other things, you can. I think probably kilo is probably good here because it's 471. You could go up to mega and have it 0.4712 mega newton meters, and of course newton meter is SI unit of work, which is a joule. So maybe we'll go it that way. So there's also megajoule is another possibility. Yeah, we'll go with that one for the crack, but I mean this is perfectly okay. But we'll go 0.4712. So 1,000 kilos is a mega, and newton meter is a joule. Okay, I think that's all I want to do there. Yeah, there's another example there, similar story, and there's another example there. Okay, so we're ready now for the final section for next week.